This is Jimmy Steele, a student of electromagnetic capstone, with the goal here of teaching how to find the electric potential and field inside a cylindrical shell, with our potentials being set to 0 at the base, 0 on the sides, and negative V naught at the top. So first of all, we want to set up our Laplace's equation that we have up here, where the Laplacian times the operating on the voltage gives us 0. The Laplacian in cylindrical coordinates is mostly straightforward except for this scary term. But it's nothing that anybody can't handle in this class. Our ansatz is the product style of an ansatz, where we have a variable r for the radial term, a phi, and a z. If we evaluate this part a bit more and we multiply we input our ansatz, we get something that looks like this. And if we divide by the ansatz, we get something that looks like this. Now this term looks really scary, but let's just take it bit by bit. Now first of all, what do we know? We know that this is basically a sum of constants right here. So what could this constant be? Well, it's time to figure that out. Here we have the z term. And what this tells us is that we now have an ordinary differential equation that looks like this. Equals some constant squared. Now, if we do some trick, we could just put that over there. Now all of a sudden, wait, let's rearrange this a bit more. What do we get now? My God, we got a simple harmonic function. But what's a function that can fit this one? What is an ansatz we can put into this equation that makes it true? Well, let's head up here. We know that when z is equal to h, we have a negative v naught. But when z is 0, our potential 0. So basically, when we get to some value, we'll have a value. In z, we'll have a value. But when we're 0, we are 0. One function we could try is hyperbolic sine, written as so, with the constant right there. Let's plug this in and see if it works. So here we'll have negative k squared sine hyperbolic sine kz. And the second derivative of sine is just itself, but multiplied by the constant, of course, k squared, hyperbolic sine kz. And as we see, this satisfies both this differential equation and the boundary condition. So we can use this one. Now, it's time for this term right here. First, let's go ahead and define our v of z, or the zv. We'll set that equal to hyperbolic sine kz. We're good there. Now what do we have here? We know this one is equal to some constant squared. So let's go ahead and do that. Let's get the correct marker here. There you go. You have to apologize for the light. This is the only light I have right now. And it's a disaster, but hopefully it holds up for the remainder. So we have this expression right here. Now what we want to do right here, we want to isolate the variables. So let's go ahead and do that now. We'll multiply both sides by that s squared. S squared over here. We'll get rid of u. And s squared goes there. And we'll have an s right there. Let's go ahead and reinforce that. There we go. And make u better. There we go. Now we have this term right here. And we know this term is also going to be equal to a constant. But this expression tells us basically the curvature of this function in the phi direction is going to be some constant. As we can see though up here, voltage, or rather our potential up here, does not vary with direction. And we have no variance with direction here or here in terms of the phi component. So what we can assume here is that that constant is merely going to be 0. So we can get rid of u. In a more difficult problem, the phi term will have to stay. But for now, what we have instead is this right here. Wonderful. Now we'll multiply everything by r. And we get this. Now we have this differential equation. And it looks simple, though the solution is not so straightforward. One quick piece of backtracking here. Let's say we did vary with phi. And let's just say that it would be equal to some random constant. Well, not random, not necessarily, but hopefully the point is still understood. Let's just say it's some random constant. We'll call this a negative c squared. That would mean that that negative c squared goes in there. So it's also multiplied by that rs squared. So what we would have here, provided we had a phi term, was a rs squared, k squared minus s squared. That's what we would have here. But we do not have that. We do not have that at all. And, pardon me, I don't think that's fully correct, but we'll get back to that later on anyway. But the point is somehow that, I don't think that was entirely correct, but the c squared will go in this term somehow, but we'll go over that soon enough. But for now, we just have this to deal with. And so what solution can we make r that satisfies this differential equation? What must we set r equal to make this true? The answer to that is a special function called the Bessel function. This is to cylindrical harmonics what the Legendre polynomials are to spherical harmonics. The Bessel function looks like this. Here we have, there are many different kinds, but for the kind that we're using, j of some alpha times x is equivalent to sum from equals 0 to infinity, negative 1 to the n, n factorial, something called the gamma function. This is just a function that takes any number and gives you the factorial of it. 1 plus n plus alpha times x over 2 to the power of 2n plus alpha. This function right there is our solution. And one thing I forgot about here is that we have a constant here for the VZ. But yeah, there we go. This is our solution to that differential equation right here. Now, we can make some steps to cut it up a bit. This alpha term right here, and here, and here, this corresponds to that constant right here for the phi direction. But because we've set that to 0, we can make our lives considerably easier here. We have a J naught. It's just a gamma of 1 plus n, which actually simplifies too simply. N factorial, so we just have 2n factorials multiplied down here, and that. This is our solution to the problem here. But rather than it being an x, what we have instead of an x, we substitute a ks. That's what we do. Now there's one last thing we need to consider. Once we're going to write out this function real quick. We know our potential is equal to some constant a of n, we have a sum of course, times j naught k of s times hyperbolic sine kz. Remember our boundary conditions. We've already satisfied the z direction ones here. Now we have to satisfy the radial directions. Now how do we do that? We need to make sure that when s is a, this Bessel function goes to 0. Bessel functions are well known for the fact that they have particular values of which they become 0. Now how do we figure that out? One may remember how when solving for harmonics, we can have it so that we only want a particular value from a particular domain. So let's say we had an old problem here. Here we have this where we're potential set to 0 on both sides here. But when x equals a, our potential is 0. So we may remember something along the lines of, well, our answers could be something like a cosine times some constant x, or when x is a, this is 0. In order to achieve that, we want to make it so that our cosines work in halves. So the ansatz, or the constant rather, would look something like this. We have a 2n plus 1 over 2a. I want to see there's a pi here. That way. Anytime x equals a, these two terms go away. When n is 0, we have a pi over half. When n is 1, we have a 3 pi over half. Works in halves, gives us the zeros that we need. Something similar must be done for the Bessel function here. So, what values of ks will give us that? Again, we need to establish some kind of ratio, rather. So, when we are at Ka, we're going to have a list of x values, and there's going to be many of them that satisfy this. What this means is we can then solve for k, so we get xn over a equals k. K equals xn over a. If we plug this back into our original Bessel function, where we have j0 of, instead of k, we have xn over a times s, we get this, -1 to the n, 2 n factorials at the bottom there. And what we now get is an xns over 2a to n. There we go. And so our final solution for the potential will be, assuming that is equal to j0 of xn over a times s, which I'll just go ahead and write down here. Our potential equals the sum constant to weigh them all times j naught x m s over a times hyperbolic sine. Now that k thing corresponds here too, so xmz over a, and that's our solution. Now we'll turn it over to Nick to teach how to solve for a of n. And of course, when we want to finally take the E field, all you do is take the gradient of what that potential is.